Looking at derivatives and the algebraic approach. So if you like algebra, you're going to love this section. Um, Before we go on into the actually doing the algebra, let's kind of do a quick little recap. So graphically, when we were talking derivatives, we are talking about drawing a tangent line and getting the slope of the tangent line. Because the whole idea there was tangent lines and the graph have basically the same direction for the area around the point. Numerically, we make the interval smaller. So basically, we're calculating slope for a secant for two distinct points, and then basically we make the points come closer and closer together, and we're estimating the slope of the tangent, that's instantaneous slope, by looking at the pattern for secant as we get the points closer and closer together. And sometimes we just estimate derivatives by just using some secants, a little bit on the left side, a little bit on the right side of the point we want, and then we're just basically saying, the average, that'll be a close approximation of what happens at the point that's in the middle. But symbolically now, notation wise, we've got some different notations we could use that basically say the same thing. Slope of the tangent line, that instantaneous rate of change. So we've got f prime of x, that little derivative symbol there. We've got dy dx, and basically, which if we go over here, we have delta f over delta x. That's the change of the y values, the change of the x values. And when we take the limit as the differences in the x's go to 0, as the x values get closer and closer together, then what we have is the derivative. And then we have this big, huge, putting it all together, our derivative of f is basically the limit. That's the idea that as we interval size gets closer and closer to 0, as the interval size gets smaller, as the x values get closer together, we're basically taking the change of the f values, the change of the functions, the change of the y values over that interval size. And so that's basically the notation we're going to be playing with in the next few moments. Okay, so before we actually do an example, let's kind of look at the steps. We actually want to do the work to calculate this thing. So step number one is we need to actually come up with the formula for that top part of the fraction. So we need to come up with the formula for f of x plus h. And then the second step is we're going to make that whole numerator by subtracting out the original formula. Our next step is we're going to work that fraction. We're going to reduce out the h. And then our final step is actually do this little limit kind of thing, this notation here. And for us, we're just going to plug in 0 for h. You can take the limit by just plugging the number in for that letter. And so unless you've got some weird things happening mathematically, mostly what's happening is you just plug in the letter in, or you plug in 0 for the letter. All right, let's do an example. We're going to start off with the function 4x squared minus 1,102. And so step number one, we're going to find the formula for f of x plus h. That basically means where we saw x before, we're going to put a package deal x plus h. So we go to the original formula, it's 4x squared, and instead of x squared, we're putting the package x plus h because the x plus h is in the parentheses. And then we just do some algebra. We expand that. You may recall that x plus h squared, that quantity squared, just means x plus h times x plus h. And so that's where I'm getting the x squared plus 2xh plus h squared, is because I did that expansion. I did that multiplication. And then our next step is just multiply that 4 through. So I get the 4x squared. There's an 8xh because of the 4 and the 2. And then I get a 4 h squared. And so that's basically our formula for when we plug x plus h into the original formula. Our step number two, we need to subtract out the original formula. So we're going to take what we just built, right here from above, and then we're going to subtract out the original formula. And you'll notice the 4x squareds will cancel out because of that minus sign, and that 1102s will cancel out as well, because the minus sign here is going to make that minus sign positive, because you got a negative and a negative. And so we're left with the 8xh plus 4h squared. So that's going to be what we're going to plug into the numerator. And so we're going to end up with a fraction, and that's where we plugged in the 8xh plus 4h squared, that the work we did from the previous slide. We put that into the numerator. We have the h in the denominator, and what we're going to do is we see, hey, everybody's got an h, so we can reduce out a single h from everybody. Because this 4h squared has two h's there, we're left with our formula that we have a 4h there. We have 8x plus 4h. And then the step number 4 is actually doing the limit part. And when we're dealing with nice straightforward polynomials, we're just taking our result and we're plugging in 0 for that h. And that's how we work this limit. And what we end up with is an 8x. So our derivative is equal to 8x. So here's a first example. I went through it kind of fast, knowing that you can always hit the pause button. And so I'll have a couple more examples coming in the second part of this section on the algebraic form of the derivative. Thanks, and talk to you later.